Okay, this is 1.8 about inverses of functions. So just recall the difference between a relation and a function. This is from the beginning of our chapter. A relation is any set of related points. There are basically no restrictions on what a relation can be. But a function is a specific rule. It has rules regarding what can be a function. So a function has one output per input. And the way that we look for this is it has to pass the VLT. And if we're looking at a table or ordered pairs, it cannot have any repeated values. A one-to-one function is a function whose inverse is also a function. So the original is a function, and then its inverse is also a function. We call that one-to-one. For functions, we use the vertical line test to determine if the graph is a function. But the horizontal line test will tell us if its inverse is a function. And so this is why I'm picky on your tests and quizzes when you just say it passes the line test or it passes the straight line test. You have to tell me if it's vertical or horizontal because that means something. Okay, the horizontal line test determines if a function's inverse will also be a function, because sometimes the inverse is not. The original might be, the inverse might not be. If a function passes both vertical and horizontal line tests, it is a one-to-one function. So look at a couple examples. Is it one-to-one? So we're going to check vertical line test and horizontal line test. So for this one, passes vertical, passes horizontal. That means that yes, it is one-to-one because its function and its inverse will both be functions. This one, if we start with the vertical line test, it fails the vertical line test, meaning this can't be one-to-one because the original isn't even a function. Next one, vertical line test is good. Horizontal line test is not okay because it hits more than one point when we draw a horizontal line, so it fails the HLT, meaning that this is not a one-to-one function. Okay, vertical, good. Horizontal, good. That means that, yes, this is a one-to-one function. Okay, and the last one, vertical's fine. Horizontal, no. We hit more than one point, meaning this is not a one-to-one function. Okay, then we're going to talk about what is an inverse. So the definition of the inverse of a function is it's a function that undoes the operations of the original function. So if you had multiplication in the original, you'll have division in the inverse. If you had addition in the original, you'll have subtraction in the inverse. The graph of the inverse reflects across the line y equals x, which looks like this. It's a diagonal sort of imaginary line that passes through the origin. So the inverse will always reflect across that. And the other way to look for inverses and to decide how to graph an inverse is that the ordered pairs are reversed. So if one of our functions has an ordered pair of 5, 1, for example, so say it's like going like this. The other function would have 1, 5. So it would be like that. Okay, so it just reverses the order of the ordered pairs. Okay, inverses are not always functions. So you have to use horizontal line test, and you always have to check for domain restrictions in both the original and the inverse as you're solving. So not necessarily always a function, but we can still find the inverse if it's not a function. And we can also give domain restrictions to make sure that we are accurately representing what this inverse would look like on graph. So change f of x to y, switch x and y, solve algebraically for y. So essentially what we're doing is isolating y. So get something y equals. Then at the end you replace y with your inverse notation. And this is your inverse. Okay, just so we don't forget, we always need to check for domain restrictions on the inverse and on the original, because if we're going to talk about them, we have to talk about them in terms of they might have certain domain restrictions. So let's look at number 1. It says find the inverse of each of these functions. So number one, step one is to replace f of x with y. And then step two is to switch x and y. So we get this, x equals 4y minus 8. Once we've switched them, now we solve for y. So just using algebra, first step we'll add 8 to both sides. I'm going to move this up here. X plus 8 equals 4y. And last step is going to be divide by 4. Make sure you divide the whole other term by 4. And then the last step is to replace y with your inverse notation. And this is your inverse. Notice how the operations are opposite. So here we had 4 times x. Now we have x divided by 4. We had minus 8. Now we have plus 8. So it just flips the operations of the original. Any domain restrictions on either the original or the no? No domain restrictions, so we're good. Number 2. Any domain restrictions in my original function? This is just a quadratic, so there's no problems with denominators or square roots. So let's find the inverse. Change this to y. Then switch x and y. So we get x equals y minus 4 squared plus 6. And then solve algebraically. So subtract 6 from both sides. X minus 6 equals y minus 4 squared. How do we get rid of that squared? Square root. We're going to square root both sides to get rid of that. So we get square root of x minus 6 equals y minus 4. And then my last step is to add 4. This 4 has to be outside of your square root, so make sure you make that clear. And then we change the y to our inverse notation. Where are we going to have a domain restriction on our inverse? The square root. So remember, to talk about where we have domain issues in a square root, that radicand, the number under the radical, has to be greater than or equal to 0, right? So our domain can only be anything greater than or equal to 6. In interval notation, we would say bracket 6 to infinity. Okay? Do we have any domain restrictions in our inverse? Do we have any domain restrictions in our original? Yes. Okay, because I had a square root in my original, the domain will be restricted. X plus 2 has to be greater than or equal to 0. So x has to be greater than or equal to negative 2. So my domain is everything from negative 2 to positive infinity. But you do need to know that the inverse operation of a cubed root is what? Cubing, okay? So the inverse of a cube root is cubing. The inverse of a fifth root is to the 5th power. So those are just your opposites there. The function in its inverse will reflect, as we said earlier, over the line y equals x, and their ordered pairs will be reversed. Okay, this is the easy way. You can verify this on graph by verifying that the ordered pairs are reversed. This is the algebraic way that you would verify that an inverse and its original are actually inverses of one another. This is the harder way. This is why we did compositions. Remember that little open circle? So in order to determine if a inverse and its original are actually inverses, you compose the function and you take f of the inverse and it should simplify to x. So we'll do a couple examples, but that's the algebraic proof that a function and its inverse are indeed inverses. And then it asks us to verify algebraically. So let's call this one f of x, and we'll just say that for our sake, this is our inverse. So algebraically, this, composing the function, should simplify to x. So what we're going to do is take f of x, which is x minus 7 over 2, and wherever we see an x, we are going to plug in g of x. Remember how we compose the functions? So here we will have, like, let me plug this all in. 2x plus 7. Do you see how we plugged in the inverse into the original? Then from here, we just start to simplify. So negative 7 plus 7 gives us 0. Then we have 2x over 2. And then we can simplify and say that x equals x. When we do all that simplification, we get that the function and its inverse are indeed inverses because it simplifies to x. It asks us to find the inverse, state any domain restrictions, and then verify both algebraically and graphically. Okay? Let's start with our f of x. Okay? F of x is cubed root of x plus 2. Are there any domain restrictions on this? Cubed root? Cubed root, odd roots don't have any restrictions because you can have negatives underneath and it's fine. Okay, remember, you can graph any function by choosing x values, plugging it in, and getting out a y value. You have to know this. Okay? If we choose 3, because I always like at least 3 points graphed, perfect cubes would be like negative 8, 0, 8. Let's just do those. Okay? If we plug in negative 8 to our original, what's the cubed root of negative 8? Negative 2 plus 2 is 0. So we have 1 point at negative 8, 0. Let's graph that here. If we plug in 0, what's the cube root of 0? Plus 2 is 2. So we have another at 0, 2. And then positive 8, cube root of 8 is 2, plus 2 is 4. So we have 8, 4. Okay, so what this looks like is kind of like, I don't know, it kind of comes around from here. I don't even know. This is not the best graph. Okay, so that's our original, and it's pretty ugly. Now let's find our inverse. So to find the inverse, we're going to switch x and y. And then solve for y. How do I get rid of that cubed root? Cube. And you cube both sides. And make sure you cube the whole thing. So our inverse is x minus 2 cubed. Any domain restrictions on this? No. Okay, let's graph the inverse. I'll do it in a different color. Remember, the inverse, the ordered pairs are reversed. So if we take our y values from our original and plug those in, we should get the exact opposite order as our original. So if we do 0, 2, 4, 0 minus 2 is negative 2. Negative 2 cubed is negative 8. So we'll have 1 point at 0, negative 8. Notice how the ordered pairs are reversed. In our original, it was negative 8, 0. In our new one, it's 0, negative 8. If we plug in 2, 2 minus 2 is 0. 0 cubed is 0. So at 2, 0. Oops, not there. 2, 0. And then if we plug in 4, 4 minus 2 is 2, 2 cubed is 8. So 4, 8. And then this kind of goes like this. Okay, and so what it is reflecting across is that y equals x line, but the easier way to do it is reversing the ordered pairs. Okay, your delta will look like this, and it'll say graph the inverse. What you need to do is find clear points on this original. So like here's one at negative 6, 6. Yep, here's one at 0, 3. Here's one at 6, 0. To graph my inverse, I am going to reverse the ordered pairs. So my first point would be at 6, negative 6. So 6, negative 6. My second point would be at 3, 0. And my third point would be at 0, 6. So when you're asked to graph, you want to find very clear ordered pairs that then you can reverse their x and y and be able to graph it. Let's find 3 clearly labeled points. Okay, here's one at negative 4, 3. Here's one at 5, 0. And then, 0, 5. Okay, so if we reverse each of these ordered pairs, we get one at 3, negative 4. One at 5, 0, so this ends up covering the other one. And one at 0, 5. So our inverse is going to look like this. Okay? Okay, so this last one is just finding the inverse and then verifying that it's the inverse algebraically, making sure we know how to do this with higher order powers. So first, if we have f of x equals x to the 7th minus 9, we're going to switch x and y and say x equals y to the 7th minus 9. Then we add 9 to both sides, and we get x plus 9 equals y to the 7th. To get rid of a 7th exponent, we take the 7th root. So we'll do that on both sides. So we get the 7th root of the quantity x plus 9, and then switch out that y for our inverse function notation. So this is our inverse. And then to verify, we prove that f of our inverse equals x. So if I gave you this, f of 2, you would take 2 and you'd plug it in for x. But I didn't give you 2, I gave you f of the inverse, so we're going to plug in the inverse function that we just found to our original. So here's our original, x to the 7th minus 9. And instead of a number for x, I'm going to actually plug in the whole inverse, which is the 7th root of x plus 9. So then you can start simplifying, because this should end up all equaling x. 7th root to the 7th cancel, so that brings outside of our root x plus 9 minus 9 equals x. Then the 9's cancel, and we get that x equals x. And that is our algebraic proof that those two functions were indeed inverses of one another.